Hello, we are Smart Green, being nature at home. We are a group of 4 students from the IoT subject. Martin Londoño, Camila Tonusco, Santiago Estrada, and me, Martin Molguizo. And this is our final project. This is the index of what the project is about. First of all, the definition of it, the general features. Then we talk about the IoT development, all the stuff included in the IoT development. Then the electronics and control of all the system, and finally the building and CAD software development. What Smart Green is? Basically, we're trying to bring the nature and we bring the possibility of being nature at home. It's basically take the plants and take the nature into your own home. It's like a sustainable environment, control it with electronics to have the best quality of environment for the plants at home. And this is like the main structure and the general features of our project. First of all, we have the controlled environment, including the temperature, the humidity, light, and windfall control. And it's also powered by solar because it has a 100 watts solar source.
When it comes to the electronics and the data, we must take into account the real-time data acquisition that we're having. This is thanks to the ESP32 or the STM32 microcontrollers that we'll be using depending on availability. Then we're also using a database which is online on the cloud on a server called Supabase, which uses AWS. This will allow us to record everything online and access it no matter where we are. When it comes to the IoT development, what makes these actually Internet of Things, we must start with the local server, the MQTT broker. We made our computer into a broker to which the microcontroller will connect, will send the information by publishing to certain topics that we've predefined, and then we will have a Node.js backend. This backend will read everything that was sent to the MQTT broker on the topics, and these will modify the database accordingly. The database is the one I mentioned in Supabase, which is based on PostgreSQL. Then we of course must mention the IoT device, which has the microcontroller and all the sensors and actuators that will actually be in our construction. The cloud connection is made out of 3 components. I already explained the local server, but the online server has the Supabase database, which is Postgres based, and a railway database, a railway backend, which will be used for the front end. This will allow the front end to query the database and obtain data without connecting directly to it.
And finally, we will connect the database to the front end, which will be displayed in the visualization tool Grafana. Here we will make our requests and see in real time the states of all of the components of this project. First, we have one page that will have all the states for the sensors. Here we have luminosity, humidity, and temperature for each of the plants, and we can see how they interact over time. We also have the events page, which has some sliders that can modify our actuators. And also we have binary buttons that change our states for each valve and our pump. And we have an operation mode which defines from where we can change the information. Later we will see right now we can see the page. We can modify in real time anything. These are the sliders that when you change them, and you send submit. This goes to the database and stays there. We are using a plugin called Business Forms, and this helps us to make the sliders. Also, we can see here, whenever we do a change, for example, let's turn on this valve and let's turn off this valve, the AP code was successful, and when we refresh, the color changes. Everything is configured this way for us to know whether the change was successful or not. Now back in the presentation.
Now here we're going to talk about the electronics and the PCB that was made for the project. First we're going to start with the actuators and the variables that we need to control, then the sensors and the signal acquisition, and finally how we made the PCB and the design behind the PCB. So here we have the problem of maintaining the life of a plant. So what is needed is to have a humidity and light intensity that is controlled for the best environment so that the plant can grow and live. The actuators that we're going to use to achieve this is a water pump, two solenoid valves, and two high-powered LEDs. The control behind those power actuators is this circuit, which is a circuit made with an optocoupler that helps us isolate the logic from the powers so that the SP32 or the microcontroller doesn't get affected by the current or any sort of issues that the actuators may have.
We also have the sensor part, which already mentioned before. We have each of the important variables that are essential to the life of our plants. So here we have a humidity sensor, a light sensor, which is an LDR, and temperature sensor, that is an LM35. We do a signal treatment by having a tension follower on a little PCB done for each plant, and later we have the signal acquisition by having a low pass filter and amplification or de-amplification depending on the sensor. We also did single supply for each of the LM35A because we wanted to use only the power supply for the panel. So this greenhouse could be used anywhere in the world.
Here we have finally the PCB design. So as we can see, there are some pointers on the PCB. I'm going to go over them real quick. We have the communications part, which is isolated with its own GND or ground plane. We have the actuators connection, isolated by the optocouplers that we have here. It's as well isolated with a ground plane for itself, so that we can, so that we don't have so much noise inside the sensors and signal processing, which is on this part with its own ground plane as well. Here we have the power of the PCB. It comes in from this JST connector. Here is the microcontroller that makes the whole circuit work.
Finally, we have the building in the cab. Basically, all this product is made out of, first of all, wood. 57% of the whole building is out of MDF wood. That's like the main material we have here in the university. So is what we use here. So it's basically made first mainly out of wood, then acrylic. The ceiling is in acrylic because it's like the wind control system. It's like for avoiding the wind flow to get into the plants and affect the growing. Also, we have here some 3D printed parts. We have 12% of the whole building is out of 3D printing. Basically, it's like the fixings are made out of the 3D printing. Here, down the ceiling, we have the plants, also the lights, and we have some like the sensor housings. We have the LDR here, we have the LM35, and here we have the humidity sensor. Here we have the bulbs and the system to take the water into the plant, and this is like the main parts of our building. Here and inside this box is where we're gonna set the real PCB. We're still waiting for it because we have been having some problems with the logistic of the IoT subject, but here we have all the stuff made in prototype, electronic prototype. Then here we have like the main parts of the building. Also, if you see back the panel, here we have like the tank. Basically, the tank comes here. The problem is that as we don't have the PCB and the PCB goes here, the tank we move the tank here because it's kind of dangerous to have the water so close to the electronics. So this way we are like testing before we get the PCB. And also here, it's the battery, the pump, also connected inside the box. And all the feeders are made with aluminum screws. This is like the main idea of our building. We have like tilted the angle of the panel to get like the most amount of energy out of the sun. And that's it. This box is for electronics and water. Here are the bulbs. And this box is for the plants, it's like the controlled environment, and here is for electronics and other devices. And basically, this is our presentation, this is our project. We're still working on it, and we're still waiting for the PCB to arrive. And yeah, that's it.